All right, thank you. I'll continue along the path of biodiversity, and I present work that is done not only by me, but also by my close colleagues at Aarhus University and Tartu University in Estonia and the Technical University of Vienna. I realized that you were maybe not all biologists, so I decided to have a short background slide, just to make it easier for you to understand what my presentation is about. So it's important to understand that habitat characteristics are important for biodiversity. We simply see a strong relationship between terrain structures and vegetation structures and the biodiversity in a given site. It's also important to recognize that natural processes equals intact ecosystems, and it's hard to evaluate if the vegetation and terrain structures are natural, but it's even harder to measure the degree to which the processes that creates these structures are natural. And when I say natural processes, it's things like natural grazing, for example, done by this guy up here. It can also be natural hydrology, like when you leave the water to do whatever it likes without draining and ditching and diking and so on. But here, lidar really becomes in handy because lidar can capture the structures in the vegetation and the structures in the terrain. The study that I'm presenting included 17 different open and forest habitats, but this talk will only focus on the results of the forest part of it. And then I guess you noticed the term dark diversity in my title. So I'll just explain that to you. So that dark diversity is a relatively new concept. It's only 10 years old. It covers the part of the biodiversity that is missing in a given site. So you could also say it's the species that are absent from a given place, despite you would expect it to be there. So when I, as a biologist, walk in for example, a grassland, and I see this and this and this species, then I automatically expect this and this and this species to be there as well, because they create these communities and they sort of co-occur often. So the dark diversity it covers really the species that are not there but should be there. And this is the aims of our study. First of all, we wanted to figure out if we could to see what characterizes the habitats with a high plant dark diversity in temperate northern Europe. And this is what I call high dark diversity habitats. We also wanted to address which factors are the most important in this regard. And then we wanted to compare models using lidar alone with models where we entered also field measured data. So can we make models that are equally good to the field measured with lidar only? And this is our study area. It's all Denmark. We have close to 4,000 forest plots and the forest plots are the blue dots in this figure. And this also explains why we didn't use TLS, because we have so many different plots. We used ALS for this study with a point cloud density of 4 or 5 points per square meter, so it's even lower than AVAS. And we calculated a number of lidar measures that we entered into our models in 1.5 meter resolution. And then just to show you how the lidar measures that we used look like, this is a plot over here, and we stamped out a point cloud 30 meter radius around the center of each plot, and then we calculated all our measures within that. And if I can maybe play this, you will see, yeah. So what you can see here is that you can see the field really So the lowermost one is a local terrain variation measure, and you can really see the field over there. You can see the sharp delimitation between the very homogeneous terrain of the field and the more heterogeneous terrain of the natural area. You can also see that the terrain openness. You can see at this sort of a little hill starting there. You can see that marked also in that variable, and you can see the vegetation density in 3 different layers, and you can also see the vegetation height. You can see the trees that you see in the image as well. Let's see if that's done. And then let's move on to the forest. This is the same sized plot. It's just zoom out, so it looks smaller, but it isn't. And it's just to show you more of the lidar variables that we used. Here you can see the ditches below ground in the forest, and we calculated various measures representing the potential solar input energy to the forest. We also tried to remove the canopy to have an adjusted measure of that. And finally, you can also see the vegetation height again, just for fun here. And then I thought I would present the vegetation data as well, because I reckon that maybe some of you are interested in that. It's at least a good data set for collaborative purposes later on, maybe. We have this monitoring program in Denmark covering all the Annex 1 habitats within the European Habitats Directive, also known as the Natura 2000 habitats. And this monitoring program that we have is hierarchical, so we have these stations those are the blue ones, just an example. And within each station, which is of a similar habitat, we have a number of randomly scattered plots, primarily vegetation plots, but we also measure various other things in them, and I'll tell you in a minute. We have more than 2 million records of plants in that data set, and we have close to 4,000 forest plots in it. This is just to show you some of the habitat types, the forest habitat types in the study. The pedunculate oak forests, beech on calcareous soils, alder ash forest, and this Lutzolo fagatum beech forest is a beech forest on acidic soils. In the study we used 10 different forest habitats. Within each of the plots that I just showed you up there, we have a plant species list. We measure canopy density with a densitometer, single trees between 10 and 40, and in a larger circle, also above 40, it really resembles the Swish approach that Daniel presented this morning. We measure some soil chemistry and indicator species like, for example, this Lobaria up here. And we also register hollow trees and trees with rotten areas, and then we represent if there's some anthropogenic impacts in the circles, in the plots. Just very briefly on the methods, we used integrated nested Laplace approximation with spatial random effects because we had a lot of spatial autocorrelation in the data. And what you should note from this table is just that you can see the uppermost model, measured plus lidar, is the model including both measured variables and lidar variables, and the line up below that is a comparable model with the same n, with the same number of samples, but with only lidar data in it. And as you can see, the deviance information criterion is a little bit lower for the one with the lidar model. That means that it's actually just a tad better than the one with the measured variables. So we managed to do a model of dark diversity in these forests with lidar alone that performed at least just as well as when we included the measured variables. And finally, just the results from the other part of the analysis, and what you can translate the negative effects here is like the less of a given factor, the higher the plant dark diversity. So the less of a given factor, the more species are missing. So you can say, for example, the less bryophyte species, the more of the more plants are missing in that plot. And you can see that, just to recap, that high dark diversity forests are really characterized by being rather open and tall, and with few old growth elements, like, for example, dead wood and rat attacks. And also, as I said before, we actually made a model of dark diversity where we only used lidar, and we got a similarly good result out of it. And that's the words. I got a positive review back, so please look out for the paper in remote sensing in ecology and conservation, where I hope it gets published soon. Thank you.
Thank you very much. Any questions?
So, did I get it correctly that you used the laser metrics from the field plots and related them to the biodiversity data?
Yeah.
Have you considered the connectivity? Because you have like wall-to-wall coverage, and if you have missing species, and then I mean, a reason for that could be that they have died out locally, but they could still spread from migrate or move into that plot.
Yeah. So dark diversity can become quite philosophical, because when is the species missing? And I could entertain you with that for like half an hour at least. So no, we haven't considered that, and you could consider that, but it's actually quite hard, because then you have to do a lot of distance to nearest blah 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 calculations, and that's quite hard with so many plots that we had here.
Thank you. How did you calculate this irradiation?
This what?
Solar irradiation.
It's a formula in a paper by McCune and Kian, I think, from 2002. It just takes the aspect, the terrain aspect, it takes the slope, and it takes the latitude as inputs, and then there's a formula, you can just put it into that formula, and then you get the potential solar radiation. I'm not sure, maybe I didn't put the reference there, but you can get it from me if you want.
Hi, it was very interesting. Can I ask if you consider extending the study to the spectral diversity or optical data as well?
Yeah, I think it's a natural next step to do that, really, but so the problem is that if you want to do it in a with satellite data, you have these, it's quite local. So they are not really matching so well with, like, for example, 10-meter resolution for the Sentinel. So if I should do it, I would have to use drones or whatever, and that takes a lot to cover 4,000 plots with that. Yeah.
Okay, thank you very much.